I'm Andy Howard, an applications engineer with Keysight EEsof EDA. In this brief video, I will demonstrate an ADS workspace that runs load pull simulations on a transistor and then uses the simulated data to optimize an impedance matching network for a Doherty Power Amplifier design. Doherty Power Amplifiers are widely used in applications where high efficiency is needed over a range of output powers. I'm not going to cover Doherty PA operation in detail, but briefly, the simplest Doherty PA has a main amplifier in parallel with a peaking amplifier. The main amplifier is meant to operate at high efficiency for lower input power levels. The peaking amplifier turns on only when the input signal is near its peak amplitude, which enables Doherty PAs to deliver higher power than the main amplifier could by itself. When the peaking amplifier turns on, the load impedance seen by the main amplifier drops, which enables it to deliver more power. Thus, Doherty PAs deliver both a high output power and high efficiency over a good dynamic range of output powers. The matching network is specifically for the main amplifier transistor, but the same network could be used for the peaking amplifier. I ran load pull simulations of the main amplifier's transistor at 3 different frequencies, examined the data, then chose target load impedances that I want the matching network to generate when the peaking amplifier is off and when it is on. Then I reused the simulated load pull contours to optimize 2 different matching networks. I want to show the end results first, then I'll show the details. This shows the performance data after running the optimization that reuses data from the load pull simulations. As I mentioned, the load seen at the output of the matching network changes depending on whether the peaking amplifier is on or off. Therefore, the optimization has to be run under 2 different load conditions. The Smith charts show contours from the load pull simulations, each at a different frequency. The red contours are of output power at 3 dB gain compression. The purple X's show target impedances to be generated by the output matching network when the peaking amplifier is on. These are the high power impedances, sometimes referred to as Z-opt. The pink dots are the impedances generated by the matching network after optimization and are close to the target values. The blue contours are of efficiency and the green contours are of gain when the main amplifier device is delivering a lower but constant output power, 40 dBm in this case. You can set this to a value you want. The light blue X's show the target impedances, sometimes referred to as Z-mod, for this case when the peaking amplifier is off. The optimized matching network also generates impedances close to these target values. The lower rectangular plots show the efficiency, power, and gain versus frequency for the Z-opt loads and the efficiency and gain versus frequency for the Z-mod loads, where the output power is constant at 40 dBm. The DC IV curve schematic is used to examine the IV curves of the transistor and to help choose a bias point, given a desired operating mode and bias current. Small signal S parameters can be simulated to see the stability circles and help determine if a stability network should be added. If the load or source impedance is near the unstable region during the load pull, convergence problems or excessive gain may occur. For this transistor, near the desired fundamental frequency, the unstable region is outside the Smith chart. A basic load pull simulation should be run at a single source power level to see the approximate region to sample and to check the gain, power, and efficiency. You need to get reasonable results from this simple load pull before proceeding to the more complex load pull simulations. The more advanced load pull simulations use a data display to select the loads to sample. You can increase or decrease the point density as well as change the position and shape of the region to be sampled. Then activate the X equation to write the loads into a text file for a subsequent load pull simulation. The more advanced load pull schematic uses a data access component to read in the loads you just wrote out. For each load, it finds a preliminary gain at a power level you specify near but somewhat below the maximum gain input power, and optimizes the source power until the gain decreases by the specified amount set by the XDB target value. Then it runs a source power sweep up to the power level needed to cause the desired amount of gain compression. The result is that only the thick part of the curve is simulated. We reach the desired amount of gain compression and avoid driving the device too far into compression. In post-processing, we can interpolate the data to get various performance values at different levels of gain compression or output power. The load pull simulations have been run at 3 different source frequencies, although more or fewer frequencies could be simulated. This shows one of the data displays. The lower left Smith chart shows contours of efficiency, power delivered, and gain, all at a specified XDB gain compression point. The red X is the maximum efficiency load, and the blue X is the maximum power load. These could be used as target impedances for designing the impedance matching network. This is a more sophisticated data display. It shows contours at a specific output power on the left and at a specific gain compression on the right. Marker M1 is on the 1 dB gain compression contour and is used to select a Z mod impedance for higher efficiency at lower output power. Marker M1 could be moved closer to a higher efficiency load, but at the expense of higher gain compression. On the right Smith chart is a VSWR circle centered on the M1 marker impedance. Marker M2 is on this VSWR circle and is positioned near the maximum power load. This is the Z-opt load. When you have selected satisfactory loads using these markers, you can specify a file name and write them into a text file. The data file tool is used to write a dataset from the text file, and the dataset is used in the impedance matching network optimization. You may change what data you write out depending on the data you want to use in the optimization. In the optimization, you might start by using load pull data from only one frequency and then increase the number of frequencies. This technique of running a load pull first and then reusing the data to optimize a matching network separates the potentially computationally intensive load pull simulation from simpler linear passive network simulations during the optimization. Also, you can try different matching network topologies without having to rerun the load pull simulations. For the optimization to be successful, your matching network needs to generate reflection coefficients in the region of the simulated loads. Folder 4.0 optimizes 2 different matching networks and runs Monte Carlo simulations to help you determine roughly the nominal parameter values to use as well as their limits. You get better results if the range of reflection coefficients that can be generated is limited. The schematic reads in data from a dataset generated from a file you wrote out from one of the load pull simulations. There are 2 copies of the matching network. The upper one models the condition where the peaking amplifier is off, and the lower one models the condition where the peaking amplifier is on. For the upper case, we want the matching network to generate Z mod, and for the lower case, we want the matching network to generate Z opt. We use measurement equations to calculate the approximate midpoint of the simulated loads and optimize the matching network to generate this reflection coefficient. Then Monte Carlo simulation varies the parameter values in a uniform distribution. Increasing or decreasing the tall for tolerance variable will increase or decrease the range of reflection coefficients that are generated. This shows results from the lumped element matching network. The min and max functions show roughly the range of values you could use during one of the following more sophisticated optimizations. This shows results from a completely different matching network that uses transmission lines. This schematic attempts to optimize a matching network to just hit target impedances at one frequency. These are the purple and light blue X's and are just copied from the load pull simulation data display to this schematic, although they could be written out to a file and read in here using the data access component. This optimization is quite fast because the goals are simple. We're only trying to generate impedances and are not directly using performance data in the goals. Because this is a fast optimization, it is good to spend time here making sure your matching network can get close to these values. If it cannot, figure out why before proceeding to the more complex optimizations. This schematic has a two-step optimization. The first step optimizes nominal parameter values to hit the target impedances. Then the second optimization optimizes delta parameter values that are added to the nominal values, which allows finer adjustment to hit performance goals. For example, this shows that these second stage goals drive the performance towards higher efficiency at the expense of output power. There are also schematics for optimizing the matching network with transmission lines. Folder 4.3 has optimization schematics similar to the above, except they use target impedances at 3 frequencies and read in data at 3 frequencies. These are more realistic in their complexity, but take longer to run because there are more goals to be satisfied. This shows the optimization results. Obviously, it is more difficult to achieve performance objectives across a band of frequencies, but you can adjust the weightings on the different goals to potentially improve the optimization results. Supported customers may download this example from the Keysight EEsof Knowledge Center. There are examples that use measured load pull data to optimize impedance matching networks using the same techniques. These may also be downloaded from the Keysight EEsof Knowledge Center. If you do not have ADS, please go to this page to request a free trial.